Let's go to the fifth question of the midterm, question 5a. What is the effect of Wolff's law on the working life of artificial hips? So again, we have discussed this a lot and it is an open book, so this should be very simple. But when you listen to my answer, then maybe you can compare that small points here and there could be added or not or whatever to your answer. Wolff's law dictates that bone becomes stronger when exposed to high stress levels and weaker when stress is reduced, right? So this is Wolff's law, that if stresses are high on the bone, then it will develop strength. If stresses are low on the bone, this will not develop good strength. Now, biomaterials used in hip replacements are stronger than the bone. You see, bone is a biological material. The biomaterials could be ceramics or metals and so on, and their strength is much higher than the bone. So, once they become part of your joint, arm joint, leg joint, hip joint, then most of the load will be taken by the stronger material. This is natural, right? This is natural. So now the actual part of the bone, the natural part of the bone will take less load. So this is the problem, that the biomaterial that was there in the replacement, in the prosthetic, will take more of the load because it is stronger, and the bone will take lower load. According to Wolff's law now, if it takes lower load, then over time it will become weaker. So surrounding bones become weaker. This shortens the lifespan of the replacement. So this is a very difficult problem, but there is no easier solution to it, right? The best solution will be that we generate a biomaterial, ceramic or metal or whatever we are using in the hip replacement or other things, whose strength is very close to the strength of the natural bone. If that is there, then the natural bone and the artificial material will take similar loads, so the life of the replacement would be better. So this is the answer. Let us go to 5b. Why are most biomaterials not reused or recycled? So again, most of you got the answers right, but let me state that for you. Biomaterials are not reused or recycled for fear of transferring disease or other contamination between patients. You see, a biomaterial has been used in one patient, isn't it? It has been used. So after its useful life, if you transfer it to some other patient, then there is some contamination or some disease which you may transfer from one patient to the other. So this is one major reason. In many cases, the biomaterial was constructed specifically for one individual and would be poorly suited for other patients. So this is the other reason, that biomaterials are not generic medicines and so on. You see, biomaterial for Mr. X was for the body strength and the body plasma and the body chemistry of Mr. X. So if you want to use it for somebody else whose body chemistry and body plasma and other properties don't match it, then it will not be good for the other person. So this is the other reason. One reason was contamination. The other reason is that it was specifically designed for a special person, so it may not be exactly suitable for the other guy. So these were the two major reasons. 5c. What is biocompatibility? Why is there no single test for biocompatibility? Right? So two things. So all of you know what is biocompatibility, hopefully, right? We have discussed it at length. And why is there no single test? So first, the definition. Biocompatibility is the ability of a material to function within a host organism right, human beings, without triggering an immune response. Right? We are saying host organism because we can now use biomaterials and so on for animals also. Dogs, veterinary doctors are there, they can do it for dogs and cats and so on. So it is not only for humans, the biomaterials, it is there for other animals also. So biocompatibility simply means that this material is compatible, so it will work inside the body of this human or this animal without triggering a negative immune response. So this is biocompatibility definition. However, biocompatibility may vary considerably from person to person, and even based on location and operation of the material within a single person. Right? So biocompatibility definition is this, but this material is biocompatible for me, it is not biocompatible for you. This material is biocompatible in Oman where temperatures go to 50 Celsius. This is not biocompatible for Alaska where temperature goes to -30. So biocompatibility, the definition is there, but this extra sentence is very important to explain biocompatibility. Therefore, because of this reason, that it can vary from person to person, it can vary based on location, it can vary based on the operation. Therefore, biocompatibility may be person dependent, location dependent, and cannot be determined by a single global test. Right? So, like you see, tensile test is there, and you can take any metal, ferrous metal, non-ferrous metal, iron, steel, aluminum alloy, and you do tensile test in the same way. But you cannot devise one single biocompatibility test which is universally applicable. So the answers of the two parts of the question. Let us take a small break to do away with the monotony of the tutorial session, so that later on you can be a little more fresh. Break time again. I keep on telling you guys that, you see, if you are taking only one course with me, this mental break part is sort of easier, but if you have taken an earlier course and now you are taking a second course or a third course with me, then it becomes very, very difficult that, you see, how many decent and nice jokes and so on should I dig up so that they are not repeated. So I was trying to look at things which are more related to the current times. So this very small one, but it was really nice, related exactly to nowadays, right? The COVID-19, the pandemic all over the world, and so on. So what is the difference between lockup and lockdown? What is the difference between lockup and lockdown? In lockup, police can do bad things to you when you are inside. And in lockdown, police can do bad things to you when you are outside. Right? So just think on it. Brilliant definition of lockup and lockdown. Let us now move to quiz 3. We have solved all the questions 1 to 5, different parts of the MIT for you. So again, right, it's up to you. I mean, when the lectures are online and so on, you can pause me anywhere you like, you can take a break, you can do some portion in one time, some portion in the other time, it's up to you. But again, that request that whenever there are numerical problems and so on, then it is better to just read the question and resolve it yourself before moving on to make it more advantageous and so on. And of course, all the questions in quiz 3 and quiz 4 are directly applicable to the final exam because these materials are included in the final. Question 1. Using the isothermal transformation diagram for a 1.13 weight% carbon steel alloy shown below, determine the final microstructure in terms of micro constituents present of a specimen that has been subjected to the following time temperature treatments. In each case, assume that the specimen begins at 920 Celsius, right? Complete and homogeneous austenitic structure is there. So you know, right, this diagram is there, but you know the phase diagram of iron carbide or steel. A little above 700 Celsius, it is austenite. So any temperature of 900 or above is a complete, and it is a 1.13 weight percent carbon. So if you go to your normal steel diagram, phase diagram, and draw a vertical line on 1.13 weight percent carbon, then you will see that at 900 or so, everything is completely austenitized. So the whole steel is as an austenite at that time. And after that, you are doing the following heat treatments, right? For example, A, rapidly cool to 250, right? 1.13%, there is just one straight line, 1.13%, and it is at 900, right? So you cool all the way to 250, right? So cool to 250, hold for 103 seconds, then quench to room temperature, and so on, right? So let us see each one of them one by one. Mostly your answers were right. Some cases there might be small doubts and so on, but if you know this time temperature variation, right? Normally in a phase diagram, you do homogeneous cooling. So the cooling is done at a slow enough rate so that everything gets enough time to convert to the next one. I mean, for example, austenite changes to ferrite, austenite changes to cementite, and so on. But when you suddenly cool and then hold it at that temperature, then you get other things, and we have discussed this a lot. We have done a lot of examples on this also and so forth. So let us see.